Okay, we're recording now. So, yeah, welcome to Thursday. And just want to do a couple things. I want to go over quiz 6 and take a look at pre-lab number 2 for next week. Just walk you through it. This is a little bit more complicated than normal, so normally it won't be this intricate, but I just want to step you through it, and then also talk about the speed dependence on temperature. So let's get started. So here's quiz 6. The first one, in this case, what I'm doing now is I've given you an open organ pipe, but instead of the lowest harmonic, it's in the second harmonic. So it's a two bump pattern. And in this case, it fits a full wavelength inside the tube. So the length is equal to lambda. And if we want, I ask for the wavelength and tell you that it's 440 hertz, then the wavelength is going to be uh, just V over F. So if we use 340 and 440, we get about 0.77 meters or 77 centimeters. That's a little less than a yard. Okay. And when I use 350, I got about 85 centimeters, a little bit different. And again, that'll depend on temperature, and I'll get to that at the end of today's lecture. Okay, so again, this identification, just figuring out how many wavelengths fit into the pipe, that's going to be the key step. And then we use this formula to figure out whatever we need from there. So you're going to see that over and over again. And again, I'm not very creative. I like to reuse problems on the test, so you'll see similar things on the test. Now we want to do a closed organ pipe. And so this is a little bit more complicated, but you've seen this before. And the key here is this is 1/4 of a wavelength. Okay. So if I drew the whole wavelength, I'd go up half, down a bit, down, and then negative and round. So it would take 4 of these pipes to fit a length. So that length is only 1/4 of a wavelength. Or to turn that around, a wavelength is equal to 4 times the length. So in this case, if the pipe is 1 meter long, that's about a yard. We'll take 340 for the speed of sound. If in this case I want the frequency, it's V over lambda, and I know that's 4 times the length. So that's 4 meters over 340. I get about 85 hertz. Okay. I get about 85 hertz. And yeah, so and that's about a yard. So okay. And last one, we talked about this before, but I just wanted to reinforce this. And I apologize, I meant to put this formula on the quiz, but I asked the TA to write that up on the board because we don't want you to memorize these things. These things are on the formula sheet. So the frequency is given by this formula, but again, as scientists, we're most interested in the relationship, and it's the square root of K over M. So in this case, if M gets really big, because it's downstairs, that will make the frequency get really small. So a big M results in a small frequency. Conversely, a very stiff spring, so if K gets really big, that's upstairs, that will make the frequency go up. And then again, the amplitude is independent. It doesn't appear in this formula, so we can play loud or soft without modifying the frequency. And of course, you musicians know you can overblow an instrument and do all sorts of other things, but in the ideal case, this is it. So, and again, I apologize. I hope you had the form up on the board. If not, I'll correct for that. But we don't want you to memorize the formulas. We just want you to understand how to use them. Okay, so that's quiz 6. Let me now go to lab 2. And again, on our sheet here, if you go here to lab 2, here's the pre-lab, here's the lab. Okay, and you might want to look over the pre-lab. Sorry, you might want to look over the lab also, so you know what's going to happen. But let me step you through the pre-lab. And so here is the pre-lab. And so what we're going to do is we're going to measure the speed of sound. And we're going to use a technique similar to what Galileo tried to use 400 some years ago to try to measure the speed of light. So here's the experiment that Galileo did. And just to make the numbers work out, I didn't want the speed of light so fast, the numbers are silly. So I invented this SMU light that has a much slower speed, so the numbers come out really nice and easy. So Galileo sends his assistant 10 miles away, and he gives the assistant a lantern, and Galileo has a lantern. And so what happens is Galileo is standing over here, and his assistant standing over here. So Galileo flashes his light. Oops, lost my. Come on, there we go. Galileo flashes his light, and the light travels to the assistant. When the assistant sees the light, the assistant will flash his light back, and so the light travels back, and then Galileo measures the amount of time it took the light to travel that distance. Now, in real life, well, let's just go through the steps. So if his assistant is 10 miles away, what's important in this is to realize if he's 10 miles away, the light goes 10 miles this way, and then it comes back 10 miles. So the total distance is going to be 20 miles. Okay. And if we just do this naively, the light travels 20 miles in 20 seconds. So if I just calculate what I think to be the speed of light, I have 20 miles over 20 seconds, I get 1 mile per second. And that seems to work out. 20 miles away, 20 seconds, everything works fine. Now, when Galileo did this in real life, he was actually using the speed of light. And as you know, the speed of light is a whole lot faster. And so he was aware of the potential problem, which is the reaction time of his assistant. So when he did this, let's pretend maybe, the light came back in a second or a second and a half or something like this. And he wasn't sure whether that second or how much of that, delay was due to the actual travel time of the light and how much of it was due to the reaction time of the assistant, to see the light flash and then to turn on his flashlight to respond. So Galileo was smart enough to realize that he's got a problem here. And the difficulty is we need two pieces of information. We need the true speed of light, and we also need the reaction time of the assistant. So we need two pieces of information, but we've only made one measurement. And so that's not enough. We need to make at least two measurements if we're going to get two pieces of information out. So what Galileo did, he was a smart fellow, and he then sent his assistant, instead of 10 miles away, he sent him 20 miles away. Okay, and then he figured, okay, if I send him 20 miles away, then, I'll have two measurements and I'll be able to figure out how much is due to the reaction time of the assistant and how much is due to the true travel time of speed of light. Now, in the case of Galileo and real light, what he found is when he sent his assistant twice as far away, that it took the exact same amount of time. So basically, he concluded that the travel time of the light was so fast that it essentially took zero time for the light to travel back and forth, and all the delay was due to the reaction time of his assistant. Okay, now that we've actually been able to measure the speed of light is 186,000 miles per second. The Earth at the equator is about 25,000 miles around. So light will go around the equator something over 7 times in 1 second. So you can see that Galileo had the right idea, the right experiment. He was doing the right thing, but he just didn't have the precision to measure that. But I've made up this SMU light that has easier numbers, so we're going to work it out. So now with this SMU light, when the assistant goes 20 miles away instead of 10 miles, we now notice that the speed changes, the time changes from 20 to 30 seconds. Okay, so how can we put this together? Well, what we realize is that when we send the person farther away, the extra time is due to the extra distance. And so this is how we're going to calculate it. The true speed of light is going to be proportional to the extra distance over the extra time. And that won't involve the reaction time of the assistant, assuming it's the same in both cases. So the true speed of light is going to be extra distance over extra time. So initially it was 20 miles round trip. Now it's 40 miles round trip. The extra distance is 20 miles, and the extra time, 30 seconds minus 20 seconds, is 10 seconds. So we have 20 miles over 10 seconds. We find out that the true speed of light is 2 miles per second. Instead of up here, we got the wrong answer of 1 mile per second. Okay. So this is 2 miles per second is the true speed. Now let's go back to let's go back up here and well, as I say in part 3, let's work backwards to do a cross check and make sure we understand what's going on. Now that we know the true speed of light, let's find out how long it really took the light to travel in part 1 and how much of that was reaction time. Okay, so we come back to this problem. We come back to this problem and say, okay, the light travels a 20-mile round trip, and we decided the correct answer is 2 miles per second. A 20-mile round trip at 2 miles per second, it takes 10 seconds for the light to travel that distance. Well, if it took 10 seconds for the light to travel that distance, and we measure 20, where does the extra 10 come from? The answer is that extra 10 comes from the reaction time of the assistant. Okay, so up here we have 10 plus 10. Okay, 10 is the true travel time and 10 is the reaction time. And just as a sanity check in part 4, well, just as a sanity check, let me come down here and make sure that all lines up. Down here, you know, when he sends them 20 miles away, the total distance is 40 miles. 40 miles at 2 miles per second, it takes 20 seconds to go that distance, but we measure 30 seconds. And now we understand this 30 is 20 seconds for travel time and 10 seconds for the reaction time. And that all checks out. Up here, the 20 was 10 plus 10, 10 travel time, 10 reaction time. Down here, the 30 was 20 travel time, 10 reaction time. All right, so by making 2 measurements, we can actually figure out the right answer. Okay, and then just give a little bit of description on how you do that. Let me then switch to a plot, and this is a plot that I'm going to have you make in class. Okay, so what we found in that pre-lab was, the initial point, the XT point, it was 20 miles in 20 seconds, where we got the incorrect answer. And then it was 40 miles in 30 seconds. And then we decided that the true velocity was the extra distance over the extra time, and that gave me 2 miles per second. Okay. And then here, we found out that, if the velocity was really 2, to travel 20 miles takes only 10 seconds. So that's 10 travel time seconds, and the reaction time of the assistant is 10 seconds, and that gives us the 20. You don't have to do this for the pre-lab, but in lab, what we're going to do, we're going to plot this on a plot here where I have time on this axis and distance on this axis. And let me make that fit just a little bit. Okay. And here are the 2 points. Here are the 2 points. Okay. I've got 20 and 20, and then 30 and 40. And if you draw that carefully on graph paper and draw a straight line through it, you can figure out the time for any distance. And then the slope is going to be the velocity, because the slope is, the slope is the change in vertical of change in horizontal. That's delta x over delta t. That has units of miles per second. And the intercept is 10. And this has an interesting interpretation. What it means is that if the assistant is 0 distance away, it will take 10 seconds for this experiment. And you now realize that basically if the assistant is standing right next to you, there's of course 0 travel time for light, and the 10 seconds is simply indicating the reaction time. So by making 2 measurements, okay, the slope of this line gives the true velocity of the speed of light or the speed of sound in the case of our lab, and the intercept gives the reaction time. It says that, if the assistant was standing right next to me, it would still take 10 seconds because, of his reaction time. And of course, I made up those numbers, but they work out nicely. So that's an extra, but that's what we're going to be doing in the lab. Okay. Again, I will not, in general, I won't walk you through all of them like this. This is a little bit more complicated, but this is really the crux right here. And so step that through, and then you'll be all set to go. Especially because we're going to take air horns out in the quad and really measure the speed of sound, hopefully without disturbing the SMU police. And we'll try it out on next Monday. The last thing I want to do is talk about how the speed of sound differs as a function of temperature. And so here, this is going to be important because it's probably going to be hot outside, which is also why you want to prepare the lab in advance. So we go outside, get the measurements quick, come back in the air conditioning. But if you look in your formula sheet, and again, let me just show you where that formula sheet can be located. All right, so from our main class page, here is the formula sheet. Okay, and here's some exam review material that you may find useful. That's exam 2. Here's exam 1. There's exam, there's the formula sheet. And what we're using here is this information right here. So the speed of sound in meters per second is 332 plus or minus 0.6 meters per second per degree Celsius. And then the same thing in British system. So let's go back to that exercise. I will post this on Canvas so you have it. Yeah, so here it is off the formula sheet. It's 332 plus or minus 0.6, and that's at 0 Celsius. Okay, because in Celsius, freezing is at 0, so that's our reference point. And so let's do an example. Let's work it out at 20 degrees C. That's about 70 degrees Fahrenheit. That's about room temperature. Okay, so in this formula, we use 332, and then we take this number 0.6, and then I'm at 20 degrees C. I'll multiply this 20 times this 0.6, and 20 times 0.6 gives me 12. And let's check the units. Okay, check the units. You'll see that I have 1 over Celsius, 1 over Celsius. That cancels. I'm left with meters per second. And that way I'm really adding meters per second plus meters per second. And I've got 332 plus 12 is 344. Okay, so at room temperature, it's about 344. That's why you see I picked 350 because that's a nice round number. It's half of 700, but more commonly I'll probably round it to 340, but it could be different on different temperatures. And of course, when you go outside and it's very hot, it's going to be quite a bit higher. Just as a different example, if it's cold, if it's very cold, negative 20 degrees, it's the same formula, but now there's a negative here because I'm at negative 20, I'm at negative 20 instead of positive 20. And so that gives me negative 12. And then the speed is only 320. So you see it can vary quite a bit. And just to fill it out, here are a couple examples. You should go and fill in these tables just to make sure you understand it. But at 0 degrees C, it's 332. We figured out it was 344 at 20. And you see it goes up by 6 meters per second each time. So here to here is 6, here to here is 6. and then you add 6, 6, 6, 6, and fill in the table. Let's do the same thing in Fahrenheit. Okay, and using the British system, feet per second. Now, there's a trick here, and the important trick is that here's the formula, feet per second, and this number is 1.1 instead of 0.6 because the units are different. But in Fahrenheit, freezing is at 32 degrees. And that is our reference, and that causes a lot of problems. So to help remind you that 32 is special in the Fahrenheit system, I will typically, but not always, I will typically ask you, instead of asking you at 40 degrees, I'll ask you at 42 degrees or 52 degrees or 62 degrees. And that should tip you off that we're using the British system and you reference not to 0 Fahrenheit, but to 32 Fahrenheit. So there's an extra step. Let me walk you through that. So at 42 Fahrenheit, we have 1087 feet per second, and I multiply by 1.1 feet per second per degree Fahrenheit. And then because my reference is 32, I'm at 42, but I have to reference that to 32. So I need 42 minus 32. That gives me 10. And 10 times 1.1 is 11. And then I have 11 plus 1087 is 1098. Let's just do one more. Let's do one more. So let's do 52. Okay. And same kind of thing. Here, I have 1.1. I'm at 52. I reference that to 32. This gives me 20. 20 times 1.1 is 22. And that gives me 1109. Okay. And then here's a little table. I filled it out for the first couple, but you should go ahead and you see, for these intervals, this goes up by 11, 11, et cetera, and then you can fill that out. Okay, so you'll need to do this conversion because again, when we go outside, we're going to have to measure the outside temperature and adjust for that when we try to measure the speed of sound. Okay, so I think that will do it for today. Have a good weekend. And again, if you have any questions, I am always on email and I can also Zoom. And so good luck on the pre-lab. Again, make sure you do that before you get there because this week's a little bit more complicated, but I hope that went well and have a good weekend. Thank you. And let's see, stop the recording.